Time's a wasting. I've got in the review document, my copy of the review document, I highlighted some things that I wanted to be sure to get to. And that's what the yellow highlights are for. Let's see. I'll scroll just a little bit. See if there's a little more I can get to it. Oops, too far. There we go. That's good. Brittany.
I fill in the blank with one specific.
Okay. All right. Nail that one up there. So this first one, and I don't think these are in any kind of progressive order that we took the topics in class. So I'm just going to take them one at a time and hopefully get through them before we have to part for the day. Naturally occurring copper exists in two isotopic forms, copper 63 and copper 65. That is. Okay. So what's the approximate natural abundance of, there's more, 63.5.
I want to go to that nice thing real quick. Oh.
That's the average value, the weighted average for these two. What's the percent abundance of this one? And when we were doing this in class, we actually had decimal values for these atomic masses. But that's not given. So what we have to do for this one is assume that this one is 63 and this one's 65, which we know is not the case. Because the only one that's a whole number is which one? Carbon. Carbon's the only one that's 12 with infinite zeros. But if we don't assume that this is the value for that copper and this is the value for that copper, we're stuck. We can't get an answer. So we have to assume. So when we do the average values, we need the decimal abundance of this one. 63 times whatever it happens to be. And this fraction will tell you how much is contributed by that one. In fact, this will give us the answer to the question. But we don't want to create an equation in two unknowns because we don't have two equations to solve, right? That's how you solve an equation in two unknowns. You need two simultaneous equations, but we don't have that. So if we assume that both of these are the only isotopes, which is a big jump, but that's what we have to do. That means that this one contribution is what's left over, right? Because if this is the fractional abundance, then 1 minus x is the fraction of the other one, correct? Okay, as long as I don't lose anybody in the process. Now, this expression here equals that value, atomic mass units. Okay, so now we have an equation in one unknown. So this one's going to be 63x. This one's going to be plus 65 minus 65x equals 63.55. Everybody see how I did that? I expanded this expression to equal that value and this value. And that's still equal to this value. So now we can just continue reducing it. Let's see, this is these two have the same x. So this is going to be minus 2x. And then plus 65 equals 63.55. And then minus 2x equals this one minus that one, which would be 5. This one comes over here as a negative, so that should be a negative. So 65 minus 63, 4, yeah. And then when we solve for x, take that negative 2 over here, and that's 1.45 divided by 2, which is something I'm going to do in my head. Actually, I probably could get really close, because we do have numbers. So it's 1.45 divided by 2. Is 0.725, which in percentage terms would be what? 72.5, right? Okay. So the closest one we've got to that is 70. So it's like I always say, pick the best answer. If we had, if that was say none of the above, then you'd be perfectly justified in picking that one because it's not that one. But since it's not, the best answer is 70. Did I lose anybody? All right, that's number 1. Okay. Number 3, the average mass of carbon atom is 12.011. Carbon 12, excuse me, carbon. Just carbon. So this is a mixture of isotopes, 12.011. Assuming you were able to pick up only one carbon unit, that is one of these carbon atoms at random, the chances you would randomly get one with a mass of 12.011 would be what? What would be the probability of finding one with exactly that mass? 0. This is a weighted average. It's not, it doesn't demonstrate the mass of any one atom. Okay, sort of a trick question. Okay, 4. What's the mass of 4 atoms of copper in grams? So we're given 4 atoms. And we want to end up with so many grams. So how do we get there? What kind of problem is this? Starts with the same letters as the district attorney. It's dimensional analysis. We want to go from atoms to grams. So how do we get there? Well, what do we know about elements that will give us grams? The molar mass of the atom, right? The element. So that means we need to have it in this form in order to get to there, because that's in the numerator, that's in the numerator. So if we're talking about 4 copper atoms, we're going to get that information right over here. 63.55. Notice I'm working this problem backwards. So now we have this, we got to have something that has moles on top. Right, so it'll cancel those moles. Do we have a number or a conversion factor that will take us from atoms to moles? Right, we would need atoms on the bottom, right? And moles on the top. That way, atoms on the top, moles Atoms in the bottom would cancel. All right, what's the magic number there? Avogadro's number. So moles cancel, atoms cancel, and all we have to do, that's the thinking part. The rest is number crunching. So 4 times 63.55 divided by this huge number will give us the number of grams for 4 atoms. And in the interest of time, that's the answer. 4.22 times 10 to the minus 22nd grams. If you multiply all these out, multiply and divide, that's what you get. Okay. Something happened with the font. So this one's kind of hard to see. I'm going to just read it to you. You have a sample of zinc and a sample of argon. Zinc and argon. Okay, 2 separate samples. You have an equal number of atoms in each sample. So the number of atoms of zinc equals the number of atoms of argon. Okay. Which of the following statements concerning the masses of the sample is true? The mass of the zinc sample is more than twice as great as the mass of the aluminum sample. All right, how do we approach this problem? If you got exactly the same number of atoms of each, what's the only thing that's going to vary between the two? The mass of each atom. Right? So what's the mass of zinc? We just did that one. 60, no, we did copper, 65.38. So zinc is 65.38 atomic mass units. Actually, use this grams per mole. And argon, 40, I think, 39.95 grams per mole. Okay. Yes.
Are we supposed to be using argon or aluminum?
Is it aluminum?
It says aluminum up there, but it looks like AR from here.
Yeah, it sure does. Okay. If I don't use aluminum, it probably will come out to the same answer. Okay, let's try aluminum then. Aluminum is 23. No, 27. 26.98 grams per mole. Okay. So now if we have equal numbers, that is, we've got the same denominator in each one. In this case, it actually doesn't matter because they're ratioed to one another based upon the same number. So if the same number, that means what's the ratio of these two? Well, that's about 27, and this is about a little over 65. So 27 times 2 would be 54. Okay. That means with the same number of atoms, the zinc sample will be more than twice as massive as the aluminum sample because the ratio is greater than 2 to 1. Right? 65 is greater than 54. So let's see. First one says the mass of zinc sample. Yeah, if I continue reading the problem, it is more than twice as great as the mass of the aluminum sample. That's the right answer. You can look at the rest of them. The mass of each sample are equal. Nope. Mass of aluminum is more than. Nope. Mass of aluminum sample is more than. Nope. Mass of the zinc sample is more than the mass of the aluminum sample, but it's not twice as great. That's false also. So A is the only one that works. Let's try to emphasize the fact that the difference between the two samples is exactly caused by the mass of each individual atom. Okay, let's see. Scroll a little bit and see if I can do this. Just up here. No, too far. You know, this is more trouble than it's worth. Back. Okay, there's. We can get these two in. What's it doing there? Good. I don't know why that's in the way. Oh, I see what it's doing. Well, let me close it down. 7. The sample of ammonia has a mass of 43.5 grams. This is ammonia, 43.5 grams. How many molecules are in the sample? This is another dimensional analysis. If you've got that many grams and you go into molecules, the only bridge between mass and numbers is the molar mass. So we need the molar mass of ammonia. Nitrogen is 14.01. You can find that on the periodic table. 3 of these is 3.03. 1704. And that's grams per mole. Right? Remember, all conversion factors are equal to 1, so we can flip it if we want. And we're going to have to. 17.04 grams per mole. But that's not the end of it, because it asks for molecules. So once we got moles, we need to convert to molecules. Right? 6.022 times 10 to the 23rd. Yeah. Okay, now we got all those units canceled and we're left with molecules. If we multiply and divide all that out, we should get the answer that I don't see. D. Right. D. 1.54 times 10 to the 24. Molecules of ammonia. So how many atoms of nitrogen does that represent? Exactly the same number. Because you've got, for every one of these, you've got one of those. So if you got this many molecules, you also have that many atoms of nitrogen. How many of hydrogen would you have? 3 times that. Because for every one of these, you got 3 of those. All right, number 8. How many moles of hydrogen sulfide are contained in 49.7 grams of this gas? Okay. We don't need to stop here for very long because this is exactly the same as before, except now we're stopping at moles. We're not going to molecules. All we need is the molar mass of hydrogen sulfide. Oh, but you do need to know what the formula is. So what's the formula for hydrogen sulfide? It's got hydrogen in it, right? It's got sulfur in it. What's the ratio though? Where does sulfur come from on the periodic table? It's a chalcogen. It's an oxygen group, which means what's its charge? Times 2. Hydrogen's plus 1. So that means we need 2 of those. That will be your sticking point. If you can't write that compound, then you're stuck. Then you just need to find out what's the molar mass of sulfur. 2 times the molar mass of hydrogen, add them together and put them in here. And you can cancel grams and do your calculation. Right. Let's see, that slipped up in the scroll. All right, number 10. For which compound does 0.256 mole weigh 12.8 grams? 0.256 mole of one of those compounds weighs 12.8 grams. So first you need to know what's the target, right? Grams per mole. So we need to divide that by 0.256 moles, right? Here it is. So I get 50 grams per mole. So that's what we're comparing it to. The rest of them, you have to actually calculate their molar masses. So here we have Henry Ford again, right? C2H4O, CO2, CH3Cl, I'm pretty sure that is, and C2H6. Okay, what's the molar mass of this one? Well, carbon, 12.01 times 200. Hydrogen, 1.01 times 4. And oxygen is 16. So that's 4406. These are all grams per mole. Right? So that's not good. How about carbon dioxide? 12.01 plus 32. Right, 4401. Is that right? It's not bad, but that number's right. How about, let's see, what is this one? This is methyl chloride. So we have carbon, 12.01. Oops. It's not 12. There we go. 3 hydrogens, 3.03, and 1 chlorine. Here, look it up right here. I already remember what it is. 3545. It's 50.49. That's probably it. This is going to be 2 times 12 to 24, and then 6, right? So it's 30. Right, so this is it right here. Methyl chloride. Okay. That one, pretty much, you had to find your target, and then you had to brute force it and find out what each one of those is. How about barium sulfate? We did this one in class, didn't we? Got to be able to write barium sulfate. So you think back, say barium is this, sulfate. There's nothing in the periodic table that gives you a single element of sulfate. That's a polyatomic ion. So you'll have access to the list of polyatomics. You just have to find out that sulfate is this, has a 3- charge, and barium is what? It's an alkaline earth, which means +2. So how do you do that? Put a 2 here and a 3 there. Okay, and then you just go to the periodic table, look up 3 bariums, 2 sulfurs, 8 oxygens, and add them together. And you should get 217 grams per mole. Okay, that's 11.
Dr. Bly,
Yes.
isn't it sulfite, barium sulfite?
Yes, thank you. You read my, I don't know what happened to the font on this particular page. What would that change? Well, change this. Instead of 4, it's 3. But it doesn't change the charging. So you still have 3 over here and 2 there. Only now you have 9 oxygens instead of 12. "13. What's the mass of 6.761 mole? 6.761 mole. Sample of sodium hydroxide. All right. Unit conversion. What you need to know is what is the molar mass of this one? Grams per mole. And you can use that value as is because numerator, denominator cancel, leaves you with grams. So sodium's about 23, I think. 22.999. Oxygen 16, hydrogen's 1.01. 7, 8, 9, 10, 40. So you say 40 grams per mole times 6.761 moles. Moles cancel, leaves you with grams. It should come out to 270 grams. All right. 15. 1 molecule of a compound weighs 2.93 times 10 to the minus 22nd grams. That's the molar mass of the compound, grams per mole. No, that's molecule, excuse me. Per molecule. There we go. The molar mass of the compound is what? Well, you need a conversion factor that'll give you moles down here and cancel the molecules. Right? Molecules on top, moles on bottom. 1 mole is this, 2 times 10 to the 23rd. So that cancels the molecules, leaves you with grams per mole. This number times that number should be 176 grams per mole. Okay. There we go. Oops. There. Okay, 17. A compound is composed of element X and hydrogen. It's got probably like this. If you look at your choices here, right, these are all non-metals, so that means hydrogen's going to come first. If hydrogen came second, then the X would have to be a metal because it would be first. Remember, cations first, anions second. Okay, analysis show the compound is 80% X by mass. 80% X by mass. With 3 times as many hydrogen atoms as X. So if you have 3 times as many hydrogen atoms as X, you can get closer to the formula, right? Because this is 3 times as many of those as these, right? Ratio is 1 to 3. Which element is element X? Okay. Let's see. Am I covering up something that I need information wise? Compound being X, 3 times as many X out. It's not covering up what I need. Okay. There we go. All right, so what do we know? Well, we've got a molar mass for hydrogen. We just don't have it for the whole compound, right? It's 80% X by mass. So if we say that we have 100 grams, if we have 100 grams of that sample, that means that X is 80 grams, right? And hydrogen is 20 grams, correct? So with 20 grams of X, hydrogen, excuse me, we can find out how many moles that is. I just have 1.01 grams. Mole. There we go. So 20 divided by 1.01 is 19.8. 19.8 moles of hydrogen. All right. We also know that the ratio of moles is the same as the ratio of atoms. So if this is the number of moles of hydrogen, how many moles of X do we have? 6.6. I mean moles of X. We have this many moles of hydrogen. We have a third as many moles of X because of the ratio of 3 to 1. So now we have 80 grams per 6.6 moles. And I get 12.1 grams per mole for X. And you just look up the nearest thing you can get to that molar mass. And it turns out that it's carbon. The rest of them are nowhere near. Okay? Did I lose anybody? Okay. I knew that the only way that I could identify X was to find out what its molar mass was. Because there's no way I was going to get the number of protons out of that information. But as it turns out, we could get the molar mass from that. 18. Which compound contains the highest percent by mass of hydrogen? All right, so this one, you just have to brute force it and use inner forwarding game. Do an assembly line. Highest percentage by mass of hydrogen. So what do we need? We need what's the mass of hydrogen in each case, and then what's the total mass. So this mass of hydrogen is 1.01, this one's 2.02 grams, this one's 2.02 grams, this one's 2.02, and this one's 1.01. So now the total is going to be, for this one, we did chlorine before, it's 35.45. And then 1.01, because we This is still part of the total, so we have to add the hydrogen into that one, 3646. Okay, times 100. That's 27.7%. Hydrogen. Okay. How about this one? Water, we've done that one before, 18.02. Times 100. Is 11.2%. Okay, H2SO4, right, we got 2.02. And then we have sulfur, which is 3207. And we have 4 oxygens, which would be 64. There we go. 2.02%. That's pretty low. Sulfur is 3207 again, 32.07, and 2.02 plus. Oh, I forgot to write that number in there. It's about 98. And this one is 34.09. And that's 5.9%. And then the HF. Fluorine is 19.0 plus 1.01. Okay. And I get 5.0%. So the greatest should be HCl. No, wait a minute. What did I do wrong? Highest percent by mass of hydrogen. Ooh, that answer is wrong. Right, 1.01, 3646. Yeah, 27 cents. Shoot about that 18. Yeah, that answer is wrong. It should be A. Then we have a hard copy out. $18. I'm going to get that out. Fix it. That one, don't forget. So that's the key. 18. Should be A. That's several copies. Work problems. At least we make it work problems. Yeah, that's kind of a screwy way to work it. I don't know why I did it that way. You work problems. Okay. All right, let's get back to business here. 19. A substance contains 35 grams of nitrogen, 5.05 grams of hydrogen, 60 grams of oxygen. How many grams of hydrogen are there in a 153 gram sample? So what we need to know is what's the mass ratio for hydrogen in that sample, because that doesn't change according to the law of definite proportions. If you know the mass ratio of an element in your compound, it's the same no matter where the compound comes from. So hydrogen, 5.05 grams in the total. 5.05 plus 35 plus 60. And actually, we don't have to go all the way to percent. We just want to know the fractional amount. And I get, there, equals 0.05047 is the fractional amount of hydrogen. Well, if we have 153 grams, then the fractional amount of hydrogen will be that times 153 grams. Did I do that right? 0.0504. 153. Yeah. No, that's not right. 5 grams of hydrogen, 5 plus 35 plus 60. I think I did a calculation wrong here. Plus 5%, that's right. 5.047. 5%. So what's 5% of 153? Oh, that's better. 7.7 grams. So the closest one to that one is A. Each molecule of testosterone contains 19 atoms of carbon. The mass percent of carbon in testosterone is 79.12%. What's the molar mass of testosterone? Only 2. I'm not doing it on time. Only got a half hour left. 19 atoms of carbon per molecule. Which is 12.01 atomic mass units per atom of carbon. Now we got rid of that. Now we have this many atomic mass units of carbon. (228.19) atomic mass units of carbon per molecule. Yeah. Notice atomic mass units per molecule. Let's see. Is the same as grams per mole. Just like up here. This is atomic mass units per atom, or atomic mass units per molecule if you add them all together. And atomic mass units per atom is the same as grams per mole. So this is actually equal to 228.19 grams of carbon per mole. Okay, now we know that percent carbon is 79.12% in that molecule. Which is grams of carbon per grams of testosterone. Right, so in 100 grams of testosterone, we have 79.12 grams. So this gives us grams of testosterone per mole. And that's 288 grams per mole. Right here. That looks like an extra credit question to me, doesn't it? You? I almost stumped myself. All right, let's not waste any more time. 24, an oxide of iron has a formula of Fe3O4. What mass percent of iron does it contain? This is simple. This is one that not even I can mess up. So what do you need? If it's mass percent of iron, you need 3 times what's iron? 5585. In the numerator, and in the denominator, you have the same amount. And that's grams per mole. Plus 4 times 16 times 100. Right. The important thing to remember is you got to have iron in both the numerator and the denominator. 72%, and that looks great. Correct. Once you get started, it will stop. 26. We don't even expect you to write the compound correctly. It's given to you. So you do it the same way as that iron compound. What's percent nitrogen by mass? The trick is to recognize that there's a subscript here. So you need 2 nitrogens in the numerator. You need 2 in the denominator, 8 hydrogens, 1 chromium, 4 oxygens in the denominator. I'm gonna skip that one. All right. Hydrocarbon made solely of carbon and hydrogen is found to be 85.6% carbon. What's the empirical formula for this compound? Okay, we'll do this one. We're told that it's only carbon and only hydrogen. And the carbon is 85.6%. 85.6% carbon. So how much of it is hydrogen? Right, 14% hydrogen. How did I know that? I subtracted from 100. That's percent carbon, then what's left over is hydrogen, because we're told those are the only 2 elements in there. So where do we go from here? We got to find the empirical formula. We can't find the empirical formula from percent because percent's a dimensionless number. It's parts per 100. In this case, 85.6% would be the same as 85.6 grams in 100 grams. So if you assume 100 grams, we have 85.6 grams of carbon and 14.4% grams of hydrogen. Now we can convert it into moles. Okay. All right.
Yeah.
85.6, 12.1, 7.127. That's moles of carbon. 14.4 divided by 1.1 is 14.2. 14.26. Close enough. Moles of hydrogen. We're stuck. We need to reduce it. This is the ratio. This is the true molar ratio in the empirical formula. But we want a whole number. So which one's smaller? That one. So we divide through by the smaller number. This is equal to 1, and this is about 2. So our ratio is carbon, hydrogen, 2. Okay? All right. The empirical formula of styrene is CH. That's the empirical. And its molar mass, the molar mass of styrene is 104.1. Okay, what's the molecular formula? What are we looking for? We need a multiplier. Right, this is the empirical formula, which means that's the exact ratio, 1 to 1. So what we need to know is what's the empirical weight of this compound? 12.01, 1.01, 2, 0. Okay. how many times will 13 go into 104? 104.1 and 1302. About 8. So if we divide this one about 8 times, this is that multiplier. So that's the formula. And that'll work every time. You want to ratio the true molar mass to the empirical mass to find that multiplier. Okay. The next one's going to take too long, but we've done empirical formulas already. So for adipic acid, you set up 49.32 grams of carbon, 43.84 grams of oxygen, 6.85 grams of hydrogen, and work them out. Molar mass gives you the ratio, molar ratio, and then you have to find the whole number ratio. Divide it through by the smallest number, and then round, because lots of times they won't be exactly whole numbers. And that will give you your empirical formula. Let's see. Vitamin C contains carbon, hydrogen, oxygen, and it's known to contain 40.9% carbon and 4.58% hydrogen. So how are we going to get from there to the molecular formula? Because we're only told carbon and hydrogen, and we know there's oxygen in there too. You add carbon and hydrogen, subtract it from 100, right? That's oxygen. And then you go through the same procedure. You get the empirical formula first, then you find the empirical weight and ratio it to the true molar mass here. Find out what's the multiplier. 1, 2, 3, 4, whatever the case may be. And that's what you multiply by every subscript in your empirical formula. How many of these are true concerning balanced chemical equations? The number of molecules is conserved. The coefficients for the reactants tell you how much of each reactant you something or other. It doesn't tell you how much they are. The coefficients don't tell you how much there is. And I assume that's mass. 3. Atoms are neither created nor destroyed. Well, it's still true when the equation's balanced. Well, actually, it's balanced. It means that you have the same number of atoms of each element on either side of the equation. That's true. Coefficients indicate mass ratios. Mole ratios only, or atom ratios. 5. The sum of the coefficients on the reactant side equals the sum of coefficients on the product side? No, not necessarily. They don't have to. The only thing that has to equal is the number of atoms of the element, of each element on both sides. So only one is true, that's A. Let's see, I'm going to scroll a little bit. Yeah. In balancing equations, we change. What do we change to balance an equation? To make the number of atoms on each side of the equation balance. Coefficients. Coefficients, the number in front of each term. That's why I answered B. Oops, too far. What's the coefficient for oxygen when the following equation is balanced? Okay, we're going to balance this one. We're going to use a budget method Okay, so we start off with NH3O2 yields in O2 and H2O. Okay, so the budget method, well, first of all, are these written correctly? Of course, you assume they are because they're in the problem. That's ammonia, that's oxygen diatomic, that's nitrogen dioxide, that's water. They're written correctly. So we need to list our elements down here: nitrogen, hydrogen, oxygen. That's everybody. One nitrogen here, three oxygens, two oxygens and three hydrogens. One nitrogen, two hydrogens, and three oxygens. Okay, where are we going to start? Well, we don't need to start with nitrogen because it's already balanced. Hydrogens, how about that? Hydrogen occurs in one place here and one place there. That's a good place to start. So if you got three on this side and two on that side, hydrogen's only in one place on either side, you can use cross multiplication. So if we say 2 times this one and 3 times this one, right? 3 over here, 2 over there, that gives us 6 hydrogen here, 6 hydrogen here. Now, what has it done to the others? Well, now we have 2 nitrogens. And we have 3, 4, 5 oxygens. Right? Okay. Oh, by the way, which one are we going to save till last? Oxygen. So is it time? No, we got to get nitrogens now. So we need 2 nitrogens on this side. That makes 4 plus 3 is 7. Okay, 7 oxygens. All right, here's one we didn't cover in class: the use of fractional coefficients. You can't get 7 out of that value, right? 3 times that one would be 6, and 4 times that one would be 8. So you use a fraction. 7 halves. 7 halves of O2 gives you 7 oxygen atoms. That makes sense? Look at it this way. There's oxygen. I need 7 oxygen atoms. Right? What if I take half of that? Okay, now, so that's the half. That's half of that. Now 7 times that, I got 7 oxygens, right? Okay. But we want whole numbers. So now that we've got it balanced, right? Now this is 7. Now you get rid of the fraction. And the way you get rid of the fraction is multiply the entire thing through by 2. Right? 2 times that cancels the 2 and leaves you with 7, right? 2 times that gives 4. 2 times that is 4. And 2 times that is 6. Okay? I'll just soak it in for a second. So we have 4, 7, 4, 6 as the coefficients. Which one are we looking for? Oxygen. Coefficient of oxygen is 7. So that's C. Okay. Actually, I used 2 tricks there. One was the cross multiply. That only works if that element only occurs in one place on either side. If you got it in multiple locations, then cross multiplying just kind of muddies the water. Okay, 40. We need to stop on this. What's the sum of coefficients in the following equation using the smallest whole number? All right, you just have to balance this one again and add up the coefficients. Remembering, once you get the coefficients in place, if there are any that don't have a coefficient in front of them, they really do. They have a coefficient of 1. So don't forget to add the 1 in if there are any like that. So we'll skip that one. There's another one, sum of coefficients. This one, is a hydrocarbon combustion. Anytime you add oxygen to have oxygen with something, then it's a combustion. It's also a redox reaction, because that oxygen is going to end up in a compound here. Remember, that's one of the rules, one of the tricks. If you have an element on one side and it's in a compound on the other, you have a redox reaction. So combustions are always redox reactions. But you're going to have to use the fraction trick on this one. All hydrocarbons, except for methane, which is CH4. But if it's C2H6 or C3, no, C3H8, any of the hydrocarbons, except for methane, you'll have to use a fraction to get that oxygen to work. Okay. Let's see. This one, reaction between sodium carbonate and hydrochloric acid produces sodium chloride, carbon dioxide, and water. It's the correct set of coefficients, so it wants you to pick which one of these is the correct sequence of coefficients. And you have to write them in this order. First sodium carbonate, then hydrochloric acid, then the arrow, then sodium chloride, carbon dioxide, and water. It has to be in that order. Otherwise, you may get a balance, but it won't match these numbers. Okay? And you got to be able to write the compounds. So we won't balance it, because I know you can do that, but we'll write it out. Sodium carbonate. There's carbonate, polyatomic ion. It's a -2, so this has to be 2 there. Okay? And hydrochloric acid. Okay. Sodium chloride. Carbon dioxide. And water. So once you get those written correctly, you can budget. Notice that in this one, that's a polyatomic ion, but it's broken apart on this side, so you can't use it as a balancing unit. You have to break this one apart too. Separate carbons, separate oxygens. Take care of it that way. Quarter to 2. All right, 1:45, yeah. Okay. So if you have to go ahead. I'm gonna go ahead and keep talking until I get all these done, and then you can see it. Looks like we're recording okay. No glitches today. I had to make a substitution. If you have already looked in Brightspace, I had to make a substitution from Tuesday's lecture. How about this one? A chemical reaction has an equation 2A plus B yields C. Okay, so 2 moles of A or 2 atoms of A plus 1 of B yields 1 of C. Which one of these illustrates a stoichiometric ratio of A and B? Right, so we're going to focus on this side. We want 2 A's and 1 B ratio, 2 to 1, A to B. So it could be 2 to 1, it could be 4 to 2, it could be 6 to 3. So we look at these and see which one matches. Right? There's 1, 2, 3, 4, 5, 6, 7, 8. So 8 to 4 is the same as 2 to 1. So we know that Roman numeral 1, which is off screen here, Roman numeral 1 is correct. When we look at the others, 1, 2, 3, 4, 5, 6, 7, 8, A, and 1, 2, 3, 4, 5, 6, 7, 8. That's 1 to 1. This one is 1 to 2. And this one has C in the answer, so it can't be it. Because we're talking about a stoichiometric mixture of A and B. That's before the reaction occurs. So the only one that's true is A. It's just that first one that fits. That's to see if you remember what a stoichiometric mixture is. Okay, now we got some stoichiometry here with 46. This is a balanced equation that they've given you. What is that compound? Potassium chlorate, potassium chloride, and oxygen. So you're given 7.11 grams of potassium chlorate. How many moles of oxygen? So we want to know moles of oxygen. How do you do that? Are we stuck? No, you need the molar mass of potassium chlorate. If you get the molar mass of potassium chlorate, then you can convert to moles of potassium chloride. Now you can move. You can't move with mass. So potassium is 39.10. Okay. 39.10. Chlorine is 35.45. And 3 oxygens. Let's see, what's 3 times 16? 48. So that's 122.55. It's right here. Okay. And that gives you the number of moles. 5.80 times 10 to the minus 2 moles of potassium chlorate. Now, how do you find out how many moles of oxygen you have? Now, this assumes that all of that is converted into oxygen, 100%. You need a conversion factor that gets rid of moles on the bottom of potassium chlorate and leaves you with moles of oxygen on the top. Where do you get that ratio? There and there. .70 times 10 to the minus 2 moles of O2. Oh, it's in standard notation. Okay, minus 2. 1, 2. 0.087. Okay. That was 46. All right. 47. How many grams of calcium nitrate can be produced by reacting excess HNO3 with, gotta get that thing off there, 6.33 grams of calcium hydroxide. So we react calcium nitrate with excess HNO3. Right? Oops. Wrong. That's a product. There we go. And what is it going to produce? Calcium nitrate. That's 2. Because this is an alkaline earth, it's 2 plus. Nitrate's a minus 1. So you need 2 of them. Plus, what do you have left over? Well, recognize that this is an acid-base reaction. Right? That's an acid. That's a base. So what do you always get with an acid-base reaction? You get a salt of the cation anion for what's left over. Okay, now we need to balance it. Nitrates on both sides. Hydroxide's not. So if we put a 2 here, that gives you 2 nitrates, but it gives you 2 H's against 2 hydroxyls, which makes 2 waters. Now you can confirm this yourself, set up your budget, but I know it's true. Okay, 6.33 grams of this. 6.33. And the question is, how many grams of this can be produced? So how do we do that? Well, this is told we're at excess here, right? So we don't have to look for a limiting reactor. In fact, this is the limiting reactor. So convert that to moles. Moles of calcium hydroxide. Then convert that to calcium nitrate. Right? And you need the coefficients for these two. Well, it's 1 to 1. Okay? So the moles of calcium hydroxide is the same as the moles of calcium nitrate. So now you have moles of calcium nitrate. You just need to convert it to grams. Moles of grams. Okay, molar mass of calcium nitrate, and that gives you the moles of calcium nitrate. Okay. Let's see. For this reaction, P4O10 plus water plus yields phosphoric acid. What mass of P4O10 must be consumed if 3.71 times 10 to the 23rd molecules of water are also consumed? We're going to take a look at that. That's starting to get weak. A lot of another one. I'm losing people. Yeah.
Recording something about some lessons.
Yep. Yeah, you can go if you want. Yeah, I've already got you over. I'll just keep talking. I've done the whole lecture by myself in here before, so it won't hurt my feelings. 52. So for this reaction, P4O10 O10 plus 6 water. Nice of them, they balanced it already. Phosphoric acid. What mass of this one must be consumed if 3.71 times 10 to the 23rd molecules of water are also consumed? So in order to go from here to here, we need moles. So we take this number of molecules and convert it to moles. Molecules on the bottom. Okay. We can. 1 mole. Okay, so 6.022 divided into that. Looks like it's a little more than half. Zero 0.6167 moles water. And we want to convert that to moles of P4O10. The ratio is 6 here and 1 there. So I divide 6 into that. 0.1027 moles P4O10. I want to convert that to grams. So I need a molar mass for P4O10. So phosphorus is 3097. 30.97, actually times 4. And then 10 oxygens, 16. That's 160. That should equal to 283.88. 283.88 times that value. Negative 29.1. Yeah, 3 significant figures. Right there. Okay. All right, let's see what else we got here. 58. 5.95 gram sample of silver nitrate is reacted with barium chloride according to this equation. You get 3.17 grams of silver chloride. What's the percent yield of silver chloride? This one's pretty simple. In fact, we don't even have to put the equation up here. Actually, we do. The reason is percent yield is equal to actual divided by theoretical times 100. We know what the actual is, 3.17 grams. Right. What we don't know yet is theoretical. The theoretical will be obtained by taking this 5.95 grams and converting it to silver chloride with that form, with that balanced equation. So 5.95 grams of silver nitrate is how many moles? Because we've got to have the number of moles of this before we can go anywhere. Once we've got the number of moles of this, we can find the number of moles of that, convert it back to mass, and compare it to our actual amount. So we need silver nitrate molar mass. All right. So silver is 107.87. Nitrogen is 14.01. 3 oxygens is 48. Okay. That's 8, 8, 19, 6, 169.88. So that gives us the number of moles of silver nitrate. Which is 3.50 times 10 to the minus 2 moles of silver nitrate. Notice that the ratio here is 2 to 2 or 1 to 1. So this is also the same number of moles as silver chloride. Okay. So we just need to convert that back to grams. We need a molar mass for silver nitrate, right? Silver again is 107.87. Here it is. And we add chlorine to it. That's 143.32. Multiply that times this value, and we get 5.02. Okay, that's the theoretical amount, 5.02. Divide that into 3.17 times 100. And I get 63.2% yield Close enough. There it is right there. All right. Let's see if 59 is worth stopping at. Okay, here's a balanced equation. Methane plus chlorine yields carbon tetrachloride and hydrogen chloride gas. What mass of CCl4 will be formed if 1.2 moles of methane reacts? Okay, this is, since you're given both amounts for the reactants, for the two reactants, one of them is going to be limiting. So we need to do this one. So our equation is methane plus 4 chlorines, carbon tetrachloride, and 4 hydrogen chlorides. Okay. So we're forming from 1.2 moles of methane and 1.11 moles of chlorine. Okay. What's the mass of this one? All right. Normally what you would do is go in here and say, how much carbon tetrachloride can you form from that much methane? And do the same thing for chlorine gas. How much of this can you form from that? And that would be brute force. But if you stop and think about it, the ratio here between these two is 4 of these for every one of those. Right? So for every one of these, you need 4 of these, which means you don't have enough. What would be the stoichiometric mixture? If this is 1, then that would have to be 4.8 moles, wouldn't it? 1 to 4. But it's not. That means this one runs out first. This is limiting. So we can save ourselves a step and we don't even have to bother with that one. We just work this one. 1.11 mole of chlorine gas. Now we need to convert it to carbon tetrachloride. Right? And the ratio is 4 of these for one of those. Divide 4 into 1.11. 0.2775. Is that right? Yeah. 0.2775. No, 5, just 5. And this is, since those cancel, this is moles of carbon tetrachloride. The question is, what mass? So now we need to convert moles, grams, right? Quotient of moles and grams, molar mass. So what's the molar mass of carbon tetrachloride? Well, it's 12.01 for carbon, and then 4 times 35.45 for chlorine. $153.81 grams per mole. 153.81 grams per mole. Moles cancel these grams. So we'll multiply that one times 0.2775. And I get 42.7 grams of carbon tetrachloride. There it is. D. All right. Scroll a little bit. 61. Which of the following statements is always true concerning reaction represented by the following balanced chemical equation. Always true. Notice that of your selections here for 61, none of these statements are true is an option. So that means you got to check them all out, just in case. We have equal. If you find one of them that's true, then you can stop. If we have equal masses of C2H6 and O2, there's no limiting reaction. All right. Here's what we're going to have to do. We're going to have to take the equation, C2H6, and this is a balanced equation, 7 oxygen, H2O, and 4 carbon dioxide. Okay. If we have equal masses of this and this, there's no limiting reactant. So what's the molar mass of each one? Well, this one's 32 grams per mole. And this one is 12.01 times 2 and 6 times 1.01. So let's see what that mass is. And that's 30.08 grams per mole. All right, so this is grams per mole, but the ratio is 2 of these times 2 would be 60.08 grams. And this one would be 7 times 32. Which would be times 7 would be 224 grams. All right. So if we have equal masses of these, if you have 60 grams here and 60 grams there, then you don't have enough of this one. If you have 224 grams here and 224 grams there, you got enough of that, but you got too much of this one, right? So that's not stoichiometric. It says there is no limiting reactant. Oh yeah, there is. All right, so A has to be false. A cannot be true. How about B? If we have an equal number of moles of C2H6 and O2, there's no limiting reactant. Equal moles of each. What's the ratio? It's 2 to 7. You need 7 moles of this one to match 2 moles of that one, so B is false. How about C? If we have more mass of C2H6 than O, then O must be limiting. More mass of C2H6. Oh, okay. So if we have equal masses, this is a bad question. If you start off with equal masses, then you go to more mass of C2H6. Right? So if you have 60 here and 60 there, and you have more, which one of these is limiting if they're equal? This one is limiting. If you have more mass of this one than you have that one's still limiting. Oxygen is still limiting. So C is true. Well, we found our true one. That's it. All right. So let's see. 62, equal masses of hydrogen gas, oxygen gas are reacting to form water. Which substance is limited? All right. We might as well do this one. Equal masses of hydrogen gas and oxygen gas to produce water. Right, we need to balance that equation. Well, we need 2 oxygens over here, and now we need 4 hydrogens. That's balanced. If we have equal masses of hydrogen and oxygen, right, so we have X mass here and X mass there, same masses. Which substance is limiting? We need molar mass. Hydrogen is 2.02 grams per mole. Oxygen is 32 grams per mole. So if we have equal masses, we need 16 times as much oxygen as hydrogen by mass. So if they're equal masses, oxygen is going to be limiting. It's going to run out. Okay? If this one's 2 grams and this one's 2 grams, equal masses, that one's got to run out. All right. Let's see. Let me scroll this one down a little bit. There we go. For this reaction, there we go. Nitrogen gas and hydrogen gas makes N2H4. N2H4 is hydrazine. If the percent yield for this reaction is 82%, what's the actual mass of hydrazine produced when 25.57 grams of nitrogen react with 4.45 grams of hydrogen? Okay, this one will take a little bit of doing, but we're given the balanced equation. All right, and we're told 25.57 grams of nitrogen reacts with 4.45 grams of hydrogen. And what we want to know is, what's the actual mass of hydrazine? How much of this? Actual. And we're given the percent yield, 82% yield. Okay. So we can't use this value yet until we find out what this theoretical is. We need a theoretical, then we can compare it to the actual using that value and find out what is the actual mass of hydrazine. All right, we've got actual amounts of nitrogen and hydrogen, which means one of them is going to run out. In order to do that, we've got to find out how much hydrazine could we make from this one. So how many moles of nitrogen do we have? Grams per mole. 2 nitrogens is 28.02. Okay, so let's do a quick calculation here. And I get 0.9126 moles of nitrogen. Okay, how much of this can be produced from that? Well, what's the coefficient ratio? It's 1 to 1. So we've also got this much, 26 moles of hydrazine. Okay. Now, that's if we use all of this up. What if we use all of that up? 4.45 grams of hydrogen, grams per mole. So hydrogen is 2.02. So 4.45 and 2.02 is 2.203 moles of hydrogen, how much hydrazine is produced from that? Well, the ratio, hydrogen here, hydrazine here, that's 1, this is 2, so we take half of that. 1.101 moles of hydrazine. Now you can make the decision. Which one is limiting? This one. That's how much hydrazine is going to be produced. Okay, so now we need to convert that to mass. Moles on the bottom, right? Moles on top, moles on the bottom, grams. So hydrogen is going to be 14.01 times 2. That, and then 4.04 for the hydrogen, 3206. Okay, times 0.9126. And I get 29.3 grams of hydrazine, which is theoretical. So this yield, 82.0%, is equal to the actual, X actual, divided by 29.3 grams times 100. And we just solve for X. (24.0). X equals 24.0 grams. So there's your answer. Okay? I'm talking to myself again. All right, that was 64. 66, what's the molar mass of tetraphosphorus digoxide? This one is very easy. You just have to be able to write compound. Tetraphosphorus digoxide. 4 times phosphorus molar mass plus 10 times oxygen molar mass. That's it. No big deal. All righty. Oops, I'm going to scroll that one a little bit. There we go. 69. Which of the following samples contains the greatest number of moles of carbon atoms? In order to compare the number of moles of carbon atoms here, you're going to have to set up a Henry Ford assembly line. Greatest number of moles of carbon atoms. So you need 58 grams of this compound, H. 10. Right, so you would convert that. That will give you moles of compound. Right, you need C4H10, put it in here. And then you need the ratio of atoms to molecules. Right, so moles of C4H10, and this is moles of carbon. Right? So in this case, for every 1 mole of C4H10, you have 4 carbons. Right? So you need a value in here, divide it into that, then times 4, and you do that for each one of these. Right? For the second one, you'd use a different molar mass, and then this one would be 2 carbons for each mole of compound. Okay, you just do that for each one, then compare the numbers. And you should come out with D as the answer. '70, an unknown molecule is found to consist of 24.2% carbon, 4% hydrogen, and the remaining mass is chlorine. What's the molecular formula of the molecule given that the molar mass is found to be 150? Okay, so you know 24.2% is carbon, 4% is hydrogen. Add those together and subtract them from 100, and that's chlorine. Then you set up your assembly line, carbon, hydrogen, chlorine, convert the percentages to mass, right, for 100 grams. Convert those, ratio them to find the empirical formula, then find the empirical mass, and compare the empirical mass, ratio it to the molar mass of 150. And the ratio should give you pretty close to a whole number. That's your multiplier. Naturally occurring iron contains 5.82% iron 54, 91.66% iron 56, 2.19% iron 57, 0.33% iron 58. And then you're given the respective molar masses for each one. This one you don't have to use, like we did earlier. You don't have to use that value here. You don't have to use the mass number because you're given the values here. This one goes to that isotope, to that isotope, to that isotope, to that isotope. And you take the fractional amounts of each one that's weighted, then add them together, and that's your value right there. All right. Okay. This exercise will show you the first 3 of them, or almost the first 3. We want, what is the empirical representation of this molecule? Notice that this molecule has 1, 2, 3, 4, 5, 6 carbons and 6 hydrogens. What's the empirical formula? Well, the molecular formula is C6H6, right? C6H6. So the empirical formula would be CH. You can divide both of those through by 6 and simplify the ratio. This other one is C2H4, right? Just count up the atoms. But that one is simpler, CH2. C, let's scroll this one. Let's do both of them. Okay, C, I should have highlighted this one too. C, you have to count up each one. So you're going to find that you have carbon, hydrogen, oxygen in there. And there are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 6 carbons. Count up the hydrogens, there should be 12 of them. Count up the oxygens, there should be 6 of them. So CH2O is the empirical formula for that. Do the same thing for this one. D, count up the carbons, 1, 2, 3, 4, 5, 6. C6. H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens, and how many oxygens? 2. This one you can only simplify by dividing by 2. So 2 into that one is 1. Well, we don't write the 1. Divide this one and divide this one. C3H5O. That's your empirical formula. All righty. Let's see. Oh, okay. That was all in chapter 3. Now we're in chapter 4. So chapter 4, 1. An unknown substance dissolves readily in water, but not in benzene. And it tells you benzene is a non-polar solvent. Molecules of what type are present in the substance? Remember this, like dissolves like. So polar solutes dissolve readily in polar solvents. Non-polar solutes dissolve readily in non-polar solvents. But the twain don't mix. A non-polar solute will not dissolve in a polar solvent, and vice versa. So what you have here is if this substance dissolves in water and not in benzene, water is polar, benzene is non-polar, the solute must be polar. Here. Okay, which of the following is not a strong base? All right. So we didn't delve into this too deeply during the lecture, but strong bases are hydroxides of alkali metals or alkaline earths. So the first 2 columns will produce strong bases. You just take the element, add hydroxyls to them. Right? So this one's a strong base, this one's a strong base, this one's strong, and this one's strong. Ammonia is a weak base. Process of elimination, right? All of those other 4s are either alkaline earths or alkaline metal hydroxides. That makes them all strong. So we don't even have to know a whole lot about ammonia to know that by process of elimination, it's the only one left, and it's weak. About 6. Which of the following is paired incorrectly? Right? So how about H2SO4? Is that a strong acid? Yeah, sulfuric acid is strong. How about HNO3? Nitric acid? That's strong also. So that's incorrect. Okay. Here we have ammonia again, that's a weak base. Hydrochloric acid is strong, barium hydroxide is a strong base, right? So we found our answer. HNO3 is incorrectly labeled. It is a strong acid. The man who discovered the essential nature of acids through solution conductivity studies. We didn't talk about this a whole lot, but the man's name is Arrhenius. He was working with, he was working with acids. We're going to talk about Arrhenius in more detail when we get to chapters on acids and bases. And in fact, I think that's in the 2nd semester. But for now, it's sufficient to know that Arrhenius discovered the nature of acids. And he identified them as molecules that produce hydrogen ions in solution. When you put the compound in aqueous solution, the hydrogen dissociates and makes the acid. 9, a 16.4 gram sample of HF is dissolved in water to give 2 times 10 to the 2nd milliliters of solution. What's the concentration of the solution? All right. 16.4 grams of HF in what? 2.0 times 10 squared milliliters. Right. Notice from the answers that your answers have to be in molarity. Remember, molarity, see, let's put it down here. Molarity is equal to moles per unit volume, and the volume has to be in liters, and that's automatically moles. So this has to be converted to liters, right? So we can do it two ways. We can move the decimal place to the left. I think that's right. Let's see. 200 milliliters, yes, is 0.2 liters. You can check me out and see if that's right. Now we need to convert this to moles. Grams on the bottom, moles on the top. HF is 1920.01. Okay. So we're going to divide 16.4, 20.01, and that's 0.8196 moles. 0.8196 moles. Divided by 0.2. So that's 4.1 molar. Right here. Okay. Takes care of that one. Oops, I should have erased that one. Chapter 4. All right. Let's see here. I sure wish I could get rid of this. Let's do this. There we go. 14. What mass of calcium chloride is needed to prepare 3.95 liters of 1.49 mole solution? So if we're working with calcium chloride, and we know the solution concentration is 1.49 molar, remember the formula, right? What do we need to know to find out the mass? We can't get the mass from the molarity. We can get the moles, but not the mass. So it's really a two-step process. If we want to get moles now, N equals M times V. So if we say this, molarity times volume, 3.950 liters. 3.950 liters. Now we can find out how many moles of calcium chloride we need. .8855 moles. Okay, so to convert moles, we know how to do that. I'm going to multiply that times this, moles on the bottom, grams on the top. We just need the molar mass of calcium chloride. So calcium is 40.08. Right? 40.08, and then 2 times 35.45. Is 110.98. So 110.98 grams per mole times 5.8855. So we need 65.3 rounded off grams of calcium chloride. Oops. Nope, my mistake. 653 grams. That's a lot. Use half a bottle of calcium chloride to make a solution. All right. 16. What mass of solute is contained in 256 milliliters of, okay. This is very repetitive, right? So I'm not going to go through this one in completion. You know the molarity. You know the volume, but you need to convert the volume to liters, right? So if you say molarity times the volume equals the moles of your ammonium chloride. And then you convert the moles to mass using the molar mass of ammonium chloride, and that's your answer. Okay. .28 gram sample of barium hydroxide is dissolved in enough water to make 2.45 liters. How many milliliters of this solution must be diluted with water in order to make 1 liter of 0.1 molar barium hydroxide? Okay, this is a dilution experiment. But you got to find out what is the concentration first. Right, what's the molarity of that solution? Then you can use M1V1 equals M2V2. You got to do this one first. 74.28 grams of barium hydroxide. Right, so we're going to convert that to moles. Barium hydroxide. We need 1 barium, 137.33. 2 oxygens, and 4 hydrogens. Oops, excuse me, 2 hydrogens, sorry. All right, 2.02, 32, 137.33. There. So this is 171.35 divided into 74.28. And I get 0.4335 moles of barium hydroxide. Okay, now that we have moles of barium hydroxide and we have liters of final solution, uh, 450, that will give us the molarity. .1769 molar. Is that right? Let's see if I did this right. Yep. Yep. Okay, so that's the molarity here. 0.1769 molar. That's the concentrated one. So that's our unknown. And we want to end up with 0.1 molar, 1 liter. Okay. So to get this one, we take 0.1 and divide by that value. And I get volume. This is in milliliters. Right. So this volume first is going to be in liters. 5, 6, 5. And milliliters is 565. That's liters. This is milliliters. So there's your answer right there. All right, what volume of 18 molar sulfuric acid must be used to prepare 2.3 liters of 0.145 molar? This is simpler than 17. What you need is to set up a table on the left and say, what do we know? Well, we know this one's 18 molar concentrated, but we don't know what the volume is. What volume of that concentrated acid must be diluted? And the molarity of the finished product is 2.3. No, excuse me, that's the volume. 2.30 liters of 0.145 molar. Okay. The answer is in milliliters. So it may be useful to convert this to milliliters. Let's do that. Then when you set up your dilution equation, the answer will come out in milliliters. Okay. So here we have a series that I've chosen of identifying what type of reactions you're looking at. So this 28, you have these two equations. And these are examples of what kind of reaction. Notice that this one is aqueous, this one's aqueous, that product is aqueous, that product is solid. When you see that, you know that you have a precipitation reaction. Right? Is that one of the choices? Yeah, right there, precipitation. What other kind of reaction is it? Double replacement. Is that a choice though? No, there's no double replacement in here. It's not an acid base. There are no hydrogens, there's no hydroxyls. Right? So oxidation reduction. Is it an oxidation reduction reaction? Usually, a precipitation reaction is not an oxidation reduction, but that doesn't hold for every one. So what you have to do is look at the oxidation numbers. And you find out this one is 2 plus, that one's 2 plus, this one's 1 minus, that one's 1 minus. Silver is 1 plus, 1 plus, nitrate doesn't change. So we know that that is not an oxidation reduction. The only one that fits is precipitation. And if you look at this one, it's laid out the same way. Solution of a compound, a solid, and a solution. So precipitation reaction is the only one that works for both of those. Let me scroll the next one. Too much of it is hidden. There we go. So each of these reactions is what type? Notice you can use the rules, that the tricks that I gave you. There's an element, they're both in the compound. That means it's oxidation reduction, without a doubt. How about this one? There's a compound, there's an element. There's a compound with oxygen, which makes it a combustion reaction. And I said earlier, combustions are always oxidation reduction. So all three of these are oxidation reduction. Only one of them is combustion, so we can't say that all three of them are. And none of them are precipitation. So oxidation reduction is the only one that works for all three reactions. Which one of these is insoluble in water? In this case, just go to your solubility chart, right? One with the clear squares and the grayed out squares. And look at these cations versus the anions. Follow them until they meet and see if it's clear or gray. And if you do that, you'll find out that all of these are soluble in water. How about this solution of calcium nitrate and sodium phosphate? What's the formula of the solid formed in this reaction? For this one, 37. I'll do this one for you. Because you need to know how to write these compounds. Calcium nitrate. That's a polyatomic ion with a 1 mass charge, 2 plus. So this one is 2. It's aqueous. We're going to combine it with sodium phosphate. That's a 3 minus, this is a 1 plus, so you have 3 there. That's aqueous. Okay. How do you tell what the products are? Double replacement. This cation goes with that anion. This cation goes with that anion. Right? So sodium nitrate, look it up, it's soluble. Calcium phosphate. Look it up, it's insoluble. So that compound, calcium phosphate here, that one is the solid that forms from this reaction. Okay, so the next 3, the question wants us to write molecular equation and a complete ionic equation, then a net equation. So let's do these 3. Aqueous solutions of barium chloride, 38. Barium chloride, silver nitrate, yields what? Well, it tells you solid silver chloride, okay, and aqueous barium nitrate. Okay. Let's see, 2 plus, 1 minus, that's right. 1 plus, 1 minus, 1 plus, 1 minus, 2 plus, 1 minus, need 2 of them. So this is aqueous. So let's balance this. You can set up your budgeting, if you're still doing that, or you can, by inspection, we need 2 nitrates, right there. Now we need 2 silvers. That gives us 2 chlorides and 2 chlorides. We're balanced. Now, this one contains which of these terms? Silver chloride? No, because we've got a coefficient of 2. Notice that we're including the coefficients. So the term includes the coefficient. That means this one, B, is the correct one. Now the balanced complete ionic equation looks like this. This is a 2 plus. That's aqueous. We need 2 chlorides, aqueous. 2 silvers, aqueous. And 2 nitrates, aqueous. Now, why did I do that? 2 chlorides, 1 barium. 2 silvers, and 2 nitrates. Now, on the product side, you still have 2 silver chlorides solid. Doesn't break apart. Then we have 1 barium and 2 nitrates. Okay, that's your complete ionic equation. Then you look at the selection. I need to scroll just here. Let's keep going. There we go. So which ones of these match? Well, let's see. 1 silver. Oh, excuse me, this one. 2 barium, 2 plus. Nope, there's only 1 barium. Chlorides, there are 2 chlorides. B's not the answer. C, 2 silvers. Yep, 2 silver there. 2 nitrates, 1 nitrate won't work. Silver chloride aqueous, nope, never happened. Okay, so the answer is C, 2 silver ions in solution. Now for the net equation, how do we get that? We take the complete ionic equation, and we say, what's the same on both sides? Barium's the same. All right? Nitrate is the same. Now we have two chlorines, two silvers make two silver chloride, but that's not the simplest form. Right? This needs to be 1, 1, and 1. If you don't do that, then you'll get the wrong answer. Because the right answer is 1 silver in the net equation. 1 silver. There's no barium, there's no nitrate, there's no hydrogens, and there's no aqueous silver chloride. This is the only one that satisfies. All right. When solutions of strontium chloride and sodium sulfate react, which of the following is a spectator ion? Well, in order to do that, you need to know you need to see the reaction. Strontium chloride. Let's look at strontium. It's an alkaline metal. Alkaline earth, excuse me. So that means you need 2 of these. Right, that's aqueous. And sodium sulfate. Aqueous. Okay, now when they react, what do you get? Well, strontium sulfate and sodium chloride. We know sodium chloride is soluble in water. And if you look it up, strontium sulfate is a solid. Okay? So that means the strontium, the sulfate, and that are part of the net ionic reaction. And sodium and chlorine, sodium and chloride are spectators. So which ones? Well, there's a chloride ion, and there's a sodium ion, and this does 2 of these. So easy answer because there are 2 of them there that are spectators. All right, what mass of sodium hydroxide is required to react exactly with 25 milliliters of 2.7 molar H2SO4? All right. We talked about acid-base titrations, in which you have exactly the same number of hydrogen ions in the acid as you do in the base. In this case, we don't. So here's one way to do it. You need a balanced equation. Sodium hydroxide, and these are all in solution, reacting with H2SO4 yields what? Sodium sulfate plus water. Okay? So we need 2 sodiums, and 2 hydroxyls and 2 hydrogens makes 2 waters. So you can do it the budget way if you want, that's fine, but that is balanced. Okay, we're starting out with 25 milliliters of 2.7 molar H2SO4. 25 milliliters of 2.7 molar. What mass of sodium hydroxide is required? So how are we going to get mass? We've got to have moles of sodium hydroxide eventually. So how many moles of this do we have? Well, let's make it easy on ourselves. Let's just do millimoles. Just molarity times volume in milliliters. 25 times 2.7 yields 67.5 millimoles. How many millimoles of sodium hydroxide does that represent? Okay. To cancel these out, that's 1, and that's 2. So we need twice as much sodium hydroxide, molar-wise. Okay. So this cancels, and 2 times that is 135 millimoles of sodium hydroxide. Okay, so we know how much sodium hydroxide we need, but we can't convert that to grams now. So we're going to have to go to moles. So what's a millimole? Well, remember milli, 10 to the minus 3, 135 times 10 to the minus 3 moles. And then we need grams per mole. Sodium hydroxide. Sodium is 23. 23 plus 16 plus 1.01. And that's 40.01. Here we go. Times 135 exponent 3 minus times. So I get 5.40 grams. Right there. Okay. We ought to be getting close to the end by now. Oxidation states. All right, we'll do one of these. Let's do 52. Now we're probably going to have to do both of them. 52 is these are neutral molecules. That means all the oxidation states have to add up to 0. Which of the following does nitrogen have an oxidation state of +4? A, B, C, D, E. Henry Ford. NO2 and 2O, NH4, Cl, and Na, 2 minus. Okay, so what do we know? We know this one's +1 and this one's -2. We know this one's -2, -2, -1, +1. This one is -2. And this one is +1. Okay. So if this one's -2 times 3 is -6, +1 equals -5. That means nitrogen has to be +5. That's not the answer. Okay. So this one's -2 means -4 has to be balanced by nitrogen +4. That's it. That's your answer. NO2, nitrogen dioxide, has nitrogen with a +4 oxidation state. 53 says IO3 minus, the iodate polyatomic ion. The oxidation state of iodine is what? Oxygen's -2 times 3 is -6. But we need to hold one of those minuses out for that charge. So we only need to balance -5, which makes this one +5. And there it is right there. Okay, let's do 56. In this reaction, we know that's oxidation reduction because that's an element, they're both in the compound. So, which species is oxidized? Remember? Oil rig. Oxidation is loss of electrons. So who lost electrons? Well, remember these are zeros because they're elements. Over here though, that's -2 and this is +2. So which one lost electrons? There you go. Calcium is oxidized. Okay? Okay, in this reaction, chlorine is what? Let's do it. 57. We've got 2 cesiums plus chlorine gas yields 2 cesium chloride. Okay, so what's happening to chlorine? All right, these are both 0 because they're elements. This is -1 and this one's +2. So if this one goes from here to here, what happened? It gained electrons. That means it was reduced. If something is reduced, it's also an oxidizing agent because it causes the oxidation of the other species. So that in mind, chlorine is not the reducing agent, the oxidizing agent. Was it oxidized? No, it was reduced. Did it donate electrons? No, it accepted electrons. So it can't be 2 of these. The only one that works is this one right here. It's an oxidizing agent because it's the one that was reduced. Okay, I gotta scroll a little bit. I'm gonna let you do that one on your own. Okay, we can do this one. 63. Use the oxidation reduction method to balance this equation. So if we start off with iron, bromine yields Fe3 plus bromine minus. Okay, so what do? We got to find out what's the oxidation state for each one. That's 0, that's 0, that's 3 plus, that's 1 minus. So if we go from here to here, what happened? We lost 3 electrons per iron. And this one, we gained 1 electron per bromine. Okay, so we need to balance the electrons. How do you get 3 electrons out of this one? Because that's 2. If you multiply by 2, that's 4 electrons. Right? 3 electrons out of this one means, well, we can't go any further. So here's the thing. You're going to have to use a coefficient for both of them. In order to do that, you're going to have to say, 6 times that one and 3 times this one gives you 6 electrons. Okay? Because that's 6 bromines, and that's 6 bromines. So 6 electrons now, if you have 2 of these and 2 of these, that equals 6 electrons. So balancing this one, the coefficient of Br minus is 6. It's kind of a cross multiplying, except, well, you just have to make the electrons balance. There's no 2 ways about it. Select the spectator ions. We've done one of those before. I'm not going to do another one. Precipitates that form. I'm not going to do that one either. It's repetitive, right? We've already done one like that. Nitrogen had the highest oxidation state. This is the same list of nitrogen compounds as before, only now you're looking for the highest one. So you just go in there and do the oxidation states on all of them, figure out which one's the greatest. Iodine has the lowest oxidation number. Just go in and do the same thing. What's iodine? Okay, these are definitions. I'm not going to stop at those. This is a balancing equation. Yes. Let me see how much more we got and whether we're going to spend time on that. Okay, maybe we'll do these last two and actually balance the equations. Notice that I didn't subscript these. That's a subscript, that's a subscript, these are subscripts. Subscript, 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 subscript. So those are the answers. Let's see if we can get there. By the way, what reaction is this? You may not recognize that. That's nitroglycerin. Right? So when nitroglycerin decomposes explosively, it produces these gases. All right, let's see if we can make sense of this. C3H5 NO3 times. We know we got nitrogen gas, we got carbon dioxide, we got water, and we got oxygen. Okay. Nitrate's going to decompose, right? Because you don't have any nitrates over here. So we got a budget for each one: carbon, hydrogen, nitrogen, oxygen. We start off with 3 carbons, 5 hydrogens, 3 nitrogens, and 9 oxygens. On this side, we have 1 carbon, 2 hydrogens, 2 nitrogens, and 2, 3, 4, 5 oxygens. Okay. Now, we do have a free element oxygen over here, but it's also in 2 other places. So I'd focus on nitrogen as your last coefficient because it occurs nowhere else. All right, so where are we going to start? Well, we need 3 carbons. Right? 3 carbons. That makes 6, 7, 8, 9 oxygens. Okay, how about hydrogens? We got 5 here, and we can't do a 5 over here. Right, so maybe we better skip to, no, we're going to have to do it this way. 5 hydrogens. So since hydrogen occurs here and here only, we can make a 5 here and a 2 here. Right, so let's rebalance. That's 10 hydrogens. That is 6, 11, 12, 13 oxygens. And on this side, we have 6 carbons, 10 hydrogens, and 6 nitrogens, and 18 oxygens. Okay. Now for carbons, okay, we need to double our carbons again. So this is 6. That's 6 carbons, like that. And that makes 12, and 5 is 17, 18, 19 oxygens. Okay. Oxygens. Let's see, did I count this one right? 9 times 2 is 18. That's true. Okay. Here's how we can get 18 oxygens on this side. If we just take half of that one, that reduces this one to 18. Okay? Now for the nitrogens, because that's the only one left, we need 3 here. That was a trick. The fraction trick we used earlier increased the amount of the needed element. In this case, we used a fraction to decrease the amount. And now we have 1 here, plus 5 is 6, plus 12 is 18. Right, so we're balanced. Let's see if we can reduce it any further. Well, we've got to get rid of that 2. Right, so the whole thing has to be multiplied by 2. Okay, so now we need 4 of these. And we need 6 here, 12 there, 10 there, and 1 there. So it should be 4, 6, 12, 10, 1. 4, 6, 12, 10, 1. That was kind of tricky. And I suspect this one's going to have some tricks to it also. But I'm already an hour and a half over it. I think I'll show you how to balance this one in the useful information, work problems. So go in there and look at that one. I think we'll stop now.